Okay. Thank you for coming. Thanks for that introduction, Ronnie, and thank you all for turning up to see this, despite the title, which I guess was something I immediately regretted once I'd sent it off. So as Ronnie said, I'm based in the Centre for Language Evolution. We use computational models and experiments with humans and other animals to study how language evolves. And the plan for today's talk is to give you a little sample of the kind of work we do. So this talk's going to have 3 parts. In the first part of the talk, I'll tell you why we study language evolution and why we use the particular techniques we do. And then the second part of the talk, I'll give you a sample of some of the experiments we've run, showing how simple linguistic features evolve through learning and use. And then the third part of the talk, basically because I forced myself to with the abstract I wrote, I'll say what I think that implies about how language evolved in our species. In other words, how humans got language. Okay, so before I dive into the content, I have to do some acknowledgements. So all the work I'm going to present today was done in conjunction with the brilliant and photogenic people in the Centre for Language Evolution, and I couldn't have done any of this without help from these people. They're all fantastic, but in particular I want to single out one person, Simon Kirby, of the gleaming smile. So Simon, in conjunction with Jim Herford, supervised my undergraduate dissertation and then my PhD, and Simon and I have been working together for the last 20 years. And I'm looking forward to collaborating for another 20 years if you can bear it. Okay, so that's my kind of academic acknowledgement. Since this is, as well as an academic occasion, a personal occasion, I also want to thank my family, so Becky, my daughter Jessie, and my son Sam. So contrary to what this photograph suggests, they're never on my back about being away all the time, either at conferences or cycling at conferences, which sounds like it shouldn't work, but is actually the best way to do conferences. Okay, so repaying you by forcing you to come to Edinburgh and listen to me talk for 45 minutes to an hour about work is not really the way to repay you, but it's the only slot I had open in my calendar for until the end of May. Okay, so don't they look lovely? Here's some more representative photographs of the kids in actual action. Sam, you can explain this to people later on. Okay, so 3-part talk. The first part, I'm going to explain why we study language evolution and why we study it using the particular techniques that we do. Okay, so language is a system that allows open-ended communication. Any thought I can entertain in my head, I can transfer into your head using language. And that means language is an ideal tool, a well-adapted tool for the communication of knowledge and other internal states. So using language, we can convey knowledge to others about how to survive in a hostile world, or important information about social events in our community, or just information about our internal states. So this is 2 guys enjoying a Saturday night in Dunbar. And language forms the basis for human technology. So the open-ended expressive power that language provides allows us to network our intellects, share knowledge, and build on knowledge discovered by other people. And so language provides the basis for human technologies, science, and the complex social systems that make the ability to share information between individuals really pay. So all of these human behaviors, the ability to insulate ourselves from hostile environments, or to travel really fast, or to build new intelligences that one day might surpass our own, or to live in these complex structured social groups, all of those features of human behavior are dependent on the open-ended communicative power that language provides us with. But given how fantastically useful language is, you think it might be systems like language might be widespread in the natural world. In fact, only humans have language. Language is unique, and no other species has a communication system that works in this way. So all other animals communicate, but you'll find that everywhere else in the natural world, communication is quite restricted and inflexible. So chimpanzees, our closest living relatives, have quite an interesting and elaborate communication system that allows them to mediate their social interactions and communicate about food sources and danger in the environment, that kind of thing. And it works well for those purposes, but it doesn't have the open-ended expressive power that human language has. So this guy can't tell you what he did yesterday, or what he's planning to do tomorrow, or how to find a particularly profitable termite mound, or what kind of stone you need for cracking nuts. So there's stuff in his head that he can't share with other individuals using his communication system. Okay, so there's therefore a puzzle. How did language evolve? How did humans end up with this uniquely powerful open-ended system for communication? And that's our challenge as language evolution researchers, is to figure out what happened. So humans diverged from other apes between 6 and 8 million years ago. Our last common ancestors
with chimpanzees was kicking around on the planet about 6 to 8 million years ago. And since the chimpanzees, present-day chimpanzees, don't have language, then we can infer that our common ancestor with chimpanzees didn't have language either. So language must have evolved in that 6 to 8 million year time span since we diverged from chimpanzees. Okay, so what happened in that time span? One way to answer that kind of question is to try and literally dig into the past and see if we can find traces of the evolution of language in the archaeological record. But that's potentially challenging. That's not what we do, and I'll explain why that's not what we do. Okay, so one obvious problem is that language is ephemeral. As soon as you say something, it's gone, unless somebody's recording you saying it. Nowadays, we have technologies which allow us to make language permanent. So we can record stuff or we can write language down. But these are really recent, modern technical inventions. So writing's only been around for about the last 5,000 years. And since we know that language must have evolved much longer ago than that, so at least 100,000 years ago, that means that language hasn't been written down for the vast majority of its history. So language leaves no direct trace in the archaeological record. We can't see the first languages because they weren't written down. Another possibility is that even though languages, we can't see them directly, maybe we can observe in the archaeological record the machinery for producing language. Maybe we can discover the kind of physical correlates of speech. So the kind of default mode for language seems to be speech. So maybe we can look for traces of the evolution of speech in the archaeological record and then learn something about when language evolved. So when you speak, you move a bunch of stuff about in your body. That's my understanding of how it works. So this is an MRI movie of somebody speaking Finnish, as it turns out. And you can see the lips, the tongue tip, the tongue body are all moving around in this kind of intricate dance to produce speech sounds. Okay, so you have some physical apparatus for producing speech. And it'd be nice if we could dig back into the fossil record and find traces of that physical apparatus and learn something about when speech evolved. But unfortunately, we can't. All this stuff is soft tissue, and when you die, it rots away. There are some more permanent structures that might leave traces in the fossil record. There's basically some bone structures that might be associated with the ability to produce articulate speech. So some bone structure associated with the larynx, that the larynx hangs off, the hyoid bone. Maybe we can learn something about the abilities of our ancestors to produce articulate speech by studying these kinds of bones, or maybe we can learn something by studying their vertebrae and whether they would be able to do the kind of highly precise breath control that's required for producing fluent speech by studying the fossil record. But even if that's the case, and I think it's contentious, that's not going to tell us when language evolved, because not all languages are spoken. So these people are using American Sign Language. That's one of many sign languages that exist in the present day, and these are full human languages. They provide the same open-ended communicative potential as spoken languages. So even if we could track down the evolution of speech in the historical record, that wouldn't necessarily tell us about when language evolved. For instance, if the first languages were signed rather than spoken. So that seems like that's not necessarily the way to go at the moment. Another possibility you might be wondering about is, can we find other kinds of evidence, indirect evidence for language in the archaeological record? So for instance, can we find other aspects of material culture that might indicate to us that the species producing that material culture maybe had language? So this is a cave painting. It's about 15 to 20,000 years old, and it's hard to imagine that the organism that produced this kind of elaborate symbolic art didn't have language. Okay, this is really recent, right? This is only 20,000 years ago. We need to go much further back in time to get to the origins of language. And when you go further back in time to say around about 100,000 years ago, the kinds of material cultures you see at that time are much simpler. So hand axes, or relatively simple, potentially symbolic artifacts. This is a rock with a bunch of scratches on it that's been daubed in ochre. Okay, so do you need to have a language to produce these kinds of technology, or this kind of symbolic artifact? I don't know. I think you'd have a hard time convincing a skeptic that the appearance of these kinds of artifacts in the archaeological record necessarily index the origins of language. Okay, so studying the origins of language, the evolution of language, is interesting, but it's potentially challenging for all these sorts of reasons. So we take a different approach. Rather than digging back into the past, we tried to study the present in order to figure out how things would have worked in the past. So we explore the conditions under which different kinds of linguistic systems form. And we do that using computational models and experiments.
And the kind of question we ask is, what do you need to grow a language? And what does that tell you, the kind of conditions under which languages will form? What does that tell you about the likely cognitive or social capacities of our ancestors? So under what conditions would human-like languages form? Can we infer the minimal conditions under which a human-like language might form? These are things we can study in the present day rather than digging into the past. And in particular, we're particularly interested in studying how languages are shaped by the processes of learning and use. So you're not born knowing a language, you learn the language of your speech community through immersion in that language. And as you're learning that language, you also use it to communicate. So you have certain communicative goals, certain pieces of information you want to convey, or certain stuff you want people to do for you, and you achieve those goals using language. And both of those processes of learning and use shape languages. So this is something that historical linguists have known for a long time, and our idea is that you can apply those same insights, that languages are shaped by the processes of learning and use, to understand not just the kind of recent historical change of languages, but also the evolution of languages at far greater time depths. And maybe we can understand the origins of language and how language became structured as a result of understanding how languages are shaped by these processes of learning and use. And in particular, languages exist in this kind of cycle between internal representation and externalization. So you are exposed to some linguistic data, you hear people using a language or see people using a sign language, and based on that data, you learn a language. You form some knowledge of that language in your head. And then you access that language in use. You use the language to do stuff in the world. That's what Jim Herford called the arena of use. And then in so doing, as a kind of incidental side effect of trying to communicate with people, you generate linguistic data, examples of language use, which might form the basis for language learning in other individuals. So languages exist through this repeated cycle of learning and use and have persisted in this way for tens of thousands, hundreds of thousands of years. So this is the kind of process we study, and we can study learning and use in the present day, either using simulations or using experiments, as Ronnie mentioned. Okay, so that's why we study language evolution and why we use the particular techniques we do. In the second part of the talk, I'm going to give you a little sample of the kinds of techniques we use, the kinds of experiments we run. Okay, and in order to do that, I need to explain to you what I mean by language. So for my purposes, I'm going to say a language is a system for mapping between meaning and form. So I have some meaning in my head that I want to convey to you, and language gives me a way of producing some series of forms, could be spoken words or signs, that allow me to convey that meaning to you. And then, because if you share the same language as me, you can take that linguistic form that I produced and map back onto the meaning that I was trying to convey to you using that form. Okay, so a language is a system for mapping between meaning and form. That's going to include a bunch of words. So words are kind of our basic element of mapping between meaning and form. There is some concept associated with a sequence of sounds or a sign or whatever. But more interestingly, when you know a language, you don't just know the lexicon of that language, a set of words, you also know the grammar. So a grammar is a system of rules and regularities which tells you how to build and interpret complex utterances. And when you learn a language, what you do is infer from examples of language use what the underlying system of rules and regularities is. Okay, so if you know English, if you don't know English, this talk must be quite unpleasant by this point. In fact, you have to know quite a specific variety of English to understand me when I talk, apparently. But if you know English, then because you have implicitly know a system of rules and regularities that governs how words can be combined to form sentences of English, you'll know that this is a perfectly fine sentence of English, and this, despite containing the same set of words, is not a sentence of English, because it doesn't conform to the rules and regularities that govern how words can be combined in English. More interestingly, as well as just differentiating between English and not English, if you know English, you can understand the meanings that are conveyed by these sequences of words, these complex meanings, relatively complex meanings that are built up by combining parts with simpler meanings. So if you know English, if you implicitly know the system of rules and regularities that govern how complex meanings are expressed using complex forms, you know that this sentence picks out a particular kind of event in the world. And this sentence, which is superficially similar, just two of the words have swapped place, picks out a rather different kind of event in the world. Okay, and once you've acquired this system of rules and regularities explaining how you can express complex concepts using complex forms, then there's no limit to the kinds of the complexity of the ideas you can convey, or the only limits your imagination. Clearly, I'm not very imaginative, but fortunately, other speakers of English are. So this is a slightly more interesting sentence. So into the face of the young man who sat on the terrace of the Hotel Magnifique at Cannes, there had crept a look of furtive shame, the shifty hangdog look which announces that an Englishman is about to talk French. Okay, so that's a single sentence of English. Despite the fact you may never have seen that sentence before, you can quite easily construct the meaning that it conveys, because you understand the rules and regularities by which words in English can be combined in a meaningful way. Okay, so language is a system of rules and regularities governing how meaning and form map onto each other. Okay, so we need to understand how these kinds of regularities might evolve. How did language acquire this kind of rule-based structure? How did humans end up with a communication system which has these kinds of regularities embodied in it? And the hypothesis we're pursuing is that maybe these regularities can just come from the cycle of learning and use. Maybe if you have a system of meaning-form mappings that's passed from person to person via learning and use, as natural languages are, maybe somehow these kinds of regularities will naturally form through this process. So that's the kind of thing we investigate using our experiments. And our workhorse for investigating what kinds of regularities emerge from this repeated cycle of learning and use is the iterated learning experiment that Ronnie referred to in his introduction. So we do these in experiments using human participants and also in simulation, but the basic idea is the same. We take an artificial language, a miniature linguistic system that we've designed to have or lack certain properties, and we ask an individual to acquire that system, to learn it. And then they attempt to use that system to reproduce that system. And that gives us a new version of the language, which we can then use as the basis for learning in a second individual in a chain of transmission. So she's trying to learn the language produced by this guy rather than the initial language that we designed. And then after some time of learning, she'll produce a new version of that language, which we can use as the target for learning in a third individual, and so on. So we can pass these miniature languages from person to person in a kind of boring lab analog of the more fun game of Chinese whispers that you might have played when you're a kid. So you pass a piece of information from individual to individual, and you see how it changes as a result. In our case, we're not passing single sentences, but entire miniature linguistic systems from person to person. And the idea is that this gives us a kind of manageable lab analog of the way that in the wild, real languages are passed from person to person by learning and use. Okay, so this is iterated learning. We run experiments with human participants or non-human participants, and what we're looking for is how these linguistic systems change as they're passed from person to person. We also do exactly the same thing in computational simulation. So we model the same processes. We just swap our human learner users for computational learner users. And there are a number of advantages to doing this. So there's a couple of notable disadvantages for studying these processes in humans. So one is that we don't really know how humans work. And two is that we know that every participant we get into the lab will already know at least one language, which might potentially kind of change some of their behaviors in these experiments. So all the experimental results I'm going to present to you this evening are paired with matching computational experiments where we swap out humans for little simulated language learners, users, just to check that the results depend on the factors we think they depend on. In my experience, people are immediately disinterested when you start talking about computational modeling. So in this talk, I'll focus exclusively on experiments involving human participants. I guess people just like people more than they like computers. Okay, so I'm going to run you through 3 experiments looking at how different kinds of regularities emerge through this repeated cycle of learning and use, just as a consequence of a language being passed from person to person. I'm going to start with the simplest kind of experiment we do to show you how these kinds of experiments work, and then scale up quite quickly to some slightly more interesting experiments. Okay, so the first experiment I'm going to tell you about is looking at the evolution of very simple kinds of regularities in artificial languages. I've run a bunch of experiments that are essentially variants on the one I'm about to tell you about now, with all these wonderful people, and the data I'm going to present is actually from one of the first experiments we ran using this kind of paradigm. Okay, so what we do in these experiments is we get participants into the lab in this case, adult humans, and asked them to learn a miniature language which provides descriptions for events. So in this experiment, people were asked to learn a miniature language for describing events involving one or two animals performing a particular kind of movement. So this is the world you have to describe using this little miniature language. Very simple world. The reason the stimuli are so cutesy is that we also run these kinds of experiments with children, as we want stims that work for adults and kids are pickier than adults about what they'll tolerate. Okay, so you come into the lab and you're asked to learn a miniature language to describe events involving one or two animals moving, and there are a number of animals involved in these scenes. So in this case, bears, zebras, lions, and elephants. And the miniature language provides you with a little way of describing events of this sort. And as I said, this is one of the simplest kind of experiments we run. So the miniature language we're asking people to learn is very simple. So you would describe a scene like this, where there's a single elephant bouncing using a two-word sentence. So glim, that's a novel verb, and that means bounce. And then elephant, which means elephant. Okay, so we're not interested in the learning of nouns in this experiment, so we simplify that stuff away. People are quite bad at learning new words. And in this experiment, we just used familiar nouns to kind of streamline the whole learning process. Okay, so participants are trained that they can describe this kind of event using this sequence of words. And they're trained that in order to describe this kind of event, where there's multiple elephants in the scene, they have to add an extra word to the end of the sentence. So this scene would either be described glim elephant yav or glim elephant wib. Okay, so there's a novel word at the end of the sentence, and the only untidy element of this simple little artificial language is that there are two ways to mark plurality, okay, two ways to signal that there are two animals in the scene, and those two forms occur interchangeably. Okay, so you just have some optionality about how you mark plurality. Either you use yav or you use wib, and there's no rhyme or reason to which is used when. So we train participants that these two plural markers can be used interchangeably. And what we're interested in these experiments is how do participants respond to this little messy bit of this artificial language, and do they tidy it up at all? Okay, so the way these experiments work is people come into the lab, and we train them on the miniature language and then ask them to reproduce it for us. So training is very simple. They're simply exposed to events paired with their description in the miniature language. And they see multiple such presentations of events plus descriptions. Say for half an hour, you're trained on how the language works. And at the end of that phase, you move on to a testing phase where we prompt you with an event and say, give us a description for this event. And our participant produces a description for us to the best of their ability. And we test them multiple times. And the idea is that via this repeated testing, we can get an idea of how they think the language works, what they've learned about the language during the training phase. Okay. And then we plug that into this iterated learning setup. So we have an initial language that we designed that just has this one little bit of messiness, two ways of marking plurality in this case. We get our participant to learn it, and then they produce a new version of the language for us to the best of their ability. And then we take this language that our first participant produced, and we use that as the target for learning in a second individual. So she's trained on the descriptions that this guy produced, and she produces a new version of the language to the best of her ability, and we take that and pass it on to a third participant in a chain of transmission. So we just pass this little miniature language from person to person, and we're interested in what happens to that language. Does it change over time? And in particular, what happens to this little kind of unpredictable, irregular element of the language as it's passed from person to person? Okay, so quite controlled and simple experiment. Okay, so I'm going to show you results for one kind of example chain of transmission, show you what happens to this little messy plural marker, and then I'll show you some graphs with some more general results. Okay, so in this case, our participants are learning a language where we set it up at the initial generation, the initial version of the language which we designed. We set it up so that both markers could be used to mark plurality for every scene, but one marker was more common than the other. So we set it up so that 3/4 of the time you'd use wib, and 1/4 of the time you would use yav to mark plurality. And we get somebody to learn this and then reproduce a new version of the language for us, and they'll produce something like this. In general, they do a pretty good job of capturing the statistical properties of the language we trained them on. They get some differences appear between the different nouns. Some use the two markers 50-50. Some capture the frequency in their input, 75-25. Some flip that. So this participant for elephants overused yab and underused wib. But in general, it looks like our first participants are doing a pretty good job at capturing the kind of messy nature of this miniature language. Then we just take whatever our first participant produces and ask a second participant to learn it. Okay, and they'll produce a new version of the language for us, which we can call the generation 2 language. And what you'll see is that, again, they do a pretty good job of matching the input that we provided to them, but occasionally they'll exaggerate tendencies which were present in their input. So this participant is now exclusively using WIB to mark plurality when they're pluralizing zebras, and exclusively using YAV to mark plurality when they're marking plural for elephants. Okay, so the language is a little bit less variable than the language they were trained on. And these kinds of regularities are really salient to learners. So these, the fact that WIB is used exclusively for zebras and YAV is used for elephants, that really jumps out at you when you're exposed to one of these languages. And so once this feature develops in a language, it tends to stick around. So we can fast forward and look at what the language looks like after 5 generations of transmission, so after it's been filtered through 5 people's minds. And what you find reliably is that the languages end up looking like this. So you still have 2 ways of marking plurality. You still have YAV and WIB, these 2 nonsense plural markers in play, but which marker you use has become conditioned on the noun you're marking. Some nouns exclusively use WIB to mark plurality, and some exclusively use the other marker, in this case, YAV. Okay, so variation is retained in these miniature languages as they're passed from person to person, but that variation becomes predictable or conditioned on the linguistic context. Okay, so this graph shows time and generations. So generation 0 is the language we designed. Generation 1 is the participant who was trained on that language, and so on. The left-hand graph shows how often people use the majority initial marker. So initially, one of the markers is used 3/4 of the time, and as the language is passed from person to person, the percentage use of that initial marker fluctuates a bit, but it stays pretty close. And most of these chains have 2 ways of marking plurality after 5 generations. But if you look at how unpredictable your choice of marker is, given the noun you're marking, you see a steep drop-off in unpredictability. Okay, so our initial language is highly unpredictable. Every noun uses both plural markers, but rapidly as the language is passed from person to person, that unpredictable element is eliminated, and the marker choice becomes conditioned on the linguistic choice, the linguistic context becomes conditioned on which noun you're marking for a number. Okay, so just from passing a language from person to person, a simple regularity emerges. And in fact, it looks like a very simple version of a phenomenon we see in natural languages known as noun classes. Okay, so we see that in this language, 2 types of noun develop. One type of noun which mark plural using one marker, and another class of nouns which mark plural using another marker. And we see similar systems, much more complex, much more interesting systems, but nonetheless of the same basic flavor in natural languages. Okay, so if you know French, you'll be familiar with the idea that there are 2 subclasses of nouns, masculine and feminine, and they behave slightly differently syntactically. So for instance, they take different determiners. And when you learn French, you have to learn which gender each noun belongs to. Okay, so a regularity emerges through transmission, and that regularity resembles, in a very simple way, the kinds of regularities we see in natural languages. The language develops a noun class system. Okay, but this is much, the noun classes in our miniature languages are completely idiosyncratic. Okay, it's just an accident that bear ended up being pluralized with WIB and lion ended up being pluralized with YAV. In contrast, in natural languages, although there are some kind of idiosyncratic, arbitrary subcategories, or some members of those categories seem relatively arbitrary, in general, noun class systems in natural languages are quite well organized. So, for instance, in French, you can make a prediction about a noun's grammatical gender if you know something about the meaning of that word. So, for instance, in French, noun class is highly predictable based on the natural gender of the word you're referring to. So, nouns which have female reference, like the word for girl, are feminine, and nouns which have a male reference, like the word for boy, belong in the masculine grammatical class. So a semantic feature of the noun predicts the noun class of that noun, predicts something about its semantic behavior. So can we get this kind of regularity to emerge through this transmission process? Okay, so the second experiment I'm going to tell you about shows that you also get these kinds of simple, generalizable, semantically based regularities emerging through transmission of miniature languages. Okay, so basically the same experiment again, but rather than training participants on a language which allows them to label reference drawn from a single semantic category, in the first experiment this was all animals, we're now going to change the set of objects they're learning descriptions for, so that now it includes 2 salient semantic categories: animals and vehicles, or animates and inanimates, depending on how you want to think about it. And all other details of the experiment are essentially the same. So people learn descriptions for events involving these reference and then pass them on to other people through a chain of transmission. So the only change is that we've introduced a kind of salient semantic distinction. And we're interested in how that shapes the regularities that form through iterated learning. Okay, so if you look at what happens to these languages, we see that as the language is passed from person to person, variation is retained. So again, this is a graph of generation against how often they use the most frequent marker. We started these chains off at 50-50, so 2 equally frequent plural markers, and they stay pretty close to that level. So if you look at the languages at generation 5, you'll see that they contain 2 ways of marking the plural. If you look at how those plural markers are deployed, you'll see that it becomes conditioned on the semantic category of the thing that's being pluralized. So for instance, animates might be marked plural using one of the markers, and inanimates or vehicles might mark plural using the other marker. And we can capture this using mutual information. So how predictable is your choice of plural marker based on the semantic category of the thing you're marking? Our initial languages have very low mutual information, and mutual information just increases steadily as the language is passed from person to person. So this kind of natural language-like noun class system, which is based on a semantic generalization at its core, that emerges from the iterated learning process. And all we have to do to get that kind of regularity is just to add 2 salient semantic categories to the set of things that you need to talk about. Okay, so what those 2 experiments show, I think, is that simple regularities, which echo the kinds of regularities we see in natural languages, can emerge through iterated learning. And you can see the game here. We take a linguistic feature and we ask under what conditions will that linguistic feature arise through this transmission process. I get really excited about iterated learning and unpredictable variation, but almost nobody else does. Okay, so at this point you might be wondering, what about more interesting kinds of linguistic structure? Never mind noun classes, never mind those kinds of very simple regularities. What about the structure that gives language its expressive power? So earlier on, I was banging on about language's open-ended communicative power and how it underpinned basically everything that interesting that humans do. So can we see the emergence of the regularities underpin language's open-ended expressive power? Can we get those kinds of regularities to emerge through this iterated learning process? Okay, so where does language's expressive power come from? Languages have this open-ended communicative potential because they're compositional. Okay, so what that means is that if you know the meaning of an expression is a function of the meaning of its parts and the way in which they're combined. So you can build complex linguistic expressions, sentences, phrases, whatever, by combining words in our simpler units in a rule-governed way, and the meaning of the kind of complex whole is a predictable combination of the meaning of the parts, depending on the way in which they're combined. And this is what gives language its open-ended expressive power. If you understand the meaning of some basic units and the rules for combination and how the combination affects the meaning of the whole, then you can potentially generate an open-ended set of meaning-bearing utterances through that combination process. Okay, so when you learn a natural language, you don't just learn a grammar which tells you how you can stick words, say, together. You also learn how the predictable semantic effects of combining elements. And that means if you have a complex concept you want to convey, you know how to build up a sentence from simpler parts that conveys that concept. And if you hear a sentence, as long as you know the meaning of the component parts and the rules of combination, you can figure out what the complex concept that that sentence conveys is. Okay, so the open-ended expressive power of human languages comes from the fact that they're compositional, and we therefore want to understand how compositional languages evolved. So how did humans end up with a compositionally structured linguistic system? And again, the hypothesis we're going to test is that this kind of regularity, compositional structure in the mapping between meanings and forms, emerges again through this cycle of learning and use. Okay, so the final experiment I want to tell you about in this section, we just tested whether this was the case. Okay, so this is joint work with Simon, Monica Tamriz, and Hannah Cornish. What we had to do to get this to work is our simple, those very simple kind of learning and recall experiments that I told you about earlier on, they don't do the job for us. If you want to see the evolution of compositional structure, then you have to add in communicative use. Okay, so simple learning and recall, passing a language from person to person, is not enough to do the job. So in those first 2 experiments I told you about, people were using the language, but not in a very interesting sense. We just prompted them, what's the description for this? What's the description for this? What's the description for this? And they produced a description for us. So they're producing language, but they're not doing it to any end. They're not trying to communicate a particular concept. They're not using the language in communication. So in this experiment, what we did was we modified our experimental design. So after learning the miniature language, participants used it to communicate. So they weren't kind of aimlessly recalling the language because we told them to. They were using the language to meet their communicative goals. Okay, so in this paradigm, in this paper, we get participants into the lab in pairs, and then we train that pair of participants on a miniature language. Okay, and the training process works in the same way as the one I already told you about. So participants are exposed to objects paired with descriptions. So there's a slightly different set of objects. It's no longer bouncing bears and so on. So now they're learning descriptions for colored shapes paired with labels. They get multiple exposures to different kinds of shapes paired with their labels in the language they're trying to learn. So that training procedure is the same as before. Then after training, rather than simply asking them to reproduce the language for us, we get them to use it to communicate. So they come into the lab in pairs, and we get them to use that miniature language to communicate with one another. The way that works, so they interact using this miniature language. The way that works is quite simple. One participant on any given trial is prompted with an object to convey. They provide a description for that object used in the miniature language, and then we pass that description to their partner, the other participant, and they have to guess what object their partner was labeling. Okay, so they have to interpret this description. If they get it right, they get some points. If they get it wrong, they don't get any points, and the more points they get, the more chance they have of winning a bonus payment. Okay, so that motivates people to try and communicate. So now they're not just learning and then kind of aimlessly recalling the language, they're learning it and then using it to communicate. And then we take the language that one pair produced during communication, and we use that as the basis for training another pair of participants. So we pass the kind of communicative use of language from person to person. So the idea, again, is this is a kind of lab analog for the way in which real languages are transmitted through this repeated cycle of learning and use, where communicative behavior by one individual forms the basis for learning in another individual. Okay, right. So in this experiment, we're using training participants on a miniature language for labeling 12 objects. So you can see the 12 objects here. So there's 3 shapes, this kind of beanie one, flowery one, and the spiky one. And then those shapes differ in their fill pattern, so black, checked, spotty, or white. The initial language we asked our first pair of participants in each chain to learn didn't have any compositional structure. So for each object, we just generated a completely idiosyncratic label. So there was no kind of part-to-part relationship between the shape or the fill pattern and what its label looks like. Each label is simply an idiosyncratic fact that you have to memorize about each object. So this language is non-compositional. It lacks that kind of regular structure that natural languages have. Then we just run this iterated learning process. We get people to learn this language, use it to communicate, and we pass whatever they produce during communication on to the next pair of participants in the chain. Okay, so we can just fast forward through one of these chains of transmission and see how the language evolves. So initial language, first generation make a bit of a mess of it. The language jumps around and then quite rapidly settles until by Generation 6, it's developed a very simple but quite regular compositional structure, which I'll pick out for you with color highlighting. So it's gone from a non-compositional starting point to a system where the first part of each label conveys the shape, so eggy for this thing, mega mainly for this thing, and then gammony for the spiky thing. And then the second part of the label conveys the fill pattern, slightly comically, so wah-woo, wah-wah, woo-woo, for the 3 different fill patterns, and then blank if the shape is unfilled. Okay, so this language is developed just a drop of the compositional structure that at much larger scales in natural languages gives them their open-ended expressive power. And that compositional structure is developed just as a result of passing the language from pair to pair and using it during communication. This is an example of one language evolving this kind of compositional structure, and this happens fairly reliably. So if we track a bunch of such chains of transmission across generations, we can measure the extent to which those languages have compositional structure. The initial languages don't have any, and the amount of compositional structure increases as the language is passed from pair to pair. Okay, so this particularly interesting kind of regularity that we see in natural languages that is very important to understanding why natural languages work the way they do also emerges through this process of transmission as we pass a language from person to person. Okay, so we have a bunch of work using this kind of paradigm. My friend Doug Martin uses the same kind of paradigm to explore how social stereotypes might evolve. So it might not just be linguistic systems that are shaped by this iterated learning process, but also other aspects of human behavior, such as our stereotype knowledge about different social groups. We're also trying to push this paradigm to see under what conditions more complex and more interestingly structured linguistic systems might evolve. So I love these kinds of simple artificial languages, but they're definitely much simpler than human languages. And in fact, there's good reasons to expect them to be very simple. So our participants have only just learned this language. They're using it to communicate with a person they've never met before, and they're doing so in a kind of completely out of context way. And those are the conditions under which you might expect these languages to be basically as simple as possible. So in my current projects funded by the ERC, we're trying to push this paradigm to see under which conditions these languages might become more complex and might start to acquire the echoes of the kinds of complexity that we see in full-blown natural languages. Okay, but the idea again is going to be that these kinds of interesting complex structures emerge through this process of learning and use. Okay, so just to summarize part 2, the idea is that languages evolve as they're passed from person to person. And they're shaped by the processes of learning and use. And we think that some fundamental features of how natural languages work, some fundamental design features of natural language can be explained as a product simply of this iterated learning process, simply as a consequence of languages being repeatedly learned and used. Okay, so what does that tell us, or what does that imply about the evolution of language in our species? What does this tell us about how humans got language? So remember, the challenge for evolutionary linguists is to explain what happened uniquely in our lineage that gave us language that didn't happen anywhere else or to any of the other great apes. Okay, so I think we now have a partial answer to that question. So if the question is how did linguistic structure evolve, if that's what you mean by how did humans get language, how did linguistic structure evolve, I think we have an answer to that, or a good candidate answer. Linguistic structure evolves as a consequence of iterated learning of meaning form mappings, and that's what our experiments and what our computational models suggest is the case. So we've explained part of the puzzle of how language evolved in our species, or we have a mechanism that explains part of that puzzle. But of course, that just kicks the question slightly further down the road. So if iterated learning is crucial to producing structured linguistic systems, then you might want to know how the capacity for iterated learning evolved. So how did humans end up being able to transmit meaning form mappings to one another? Okay, so this is something that people are working on, but I think the experimental and computational work we've done using the iterated learning paradigm enables us to make some sensible guesses about what the answer to this question should look like. This is more speculative, but I'll tell you that and what I think about that now. Okay, so all of these experiments involve transmission of a language from person to person. And that transmission process looks something like this. An individual has a concept in their head, a meaning that they want to convey. In order to do so, they produce some linguistic form, say some sequence of words. And then based upon exposure to many such examples of language use, another person should be able to infer the compositional grammar that generated this kind of linguistic behavior that they've seen. So given enough examples, you should be able to work out the grammar that this guy has in his head that's determining how he behaves linguistically. Okay, so we can unpack that process a little bit. Okay, and this individual then has to be able to use that grammar to convey concepts to other individuals, to produce linguistic behavior that other people can learn from. Okay, so what are the kind of basic building blocks of this process? In order to do this, you have to be able to be capable of doing 3 things. You have to be capable of learning to produce novel signals. That's required to produce forms other people can observe. So you have to be able to learn how to produce these complex forms. You also have to be able to infer communicative intentions that lead people to produce forms. So the reason this guy spits out this particular sequence of sounds is that he had some meaning in his head that he wants to convey to you. In our experiments, we make the meaning of a signal really accessible. We say, here's an object, and this is the label for that object. But in the real world, you're not just given the communicative intentions that are in other people's heads. You have to infer what's driving somebody to produce this particular sequence of sounds at this particular moment in time. Okay, so that requires the ability to reason about other people's mental states and to infer communicative intentions in other people. And then when it's your turn to speak, you have to kind of flip that, and you have to reason about your interlocutor's mental states. You have to say, what do they likely know or not know, and what do I have to say to them to change their understanding of the world in the way that I want to achieve? So learning a language and also using a language involves reasoning about mental states in other individuals. If you can't do that, then you can't do iterated learning. And then finally, you have to be capable of mentally representing one of these grammars. You have to be capable of reaching the end state where you have a compositional language. What our modeling work shows is that actually you can be very, very, very reluctant to infer this kind of complex grammar, and you might only do so if your data really forces you to. So you don't have to have a predisposition to seek out this kind of structured language, but you do have to be capable of acquiring that kind of language. What our modeling and experimental work suggests is that once these three components are in place, then that enables this transmission through learning and use of meaning form mappings, and linguistic structure kind of naturally falls out of that process as a result. So if we want to understand how the capacity for language evolved in humans, then we need to explain how the capacity for iterated learning evolved in our species. So how do we end up with the ability to do these three things? Okay. Perhaps surprisingly, given the gulf between human language and the communication systems of other animals, which I kind of emphasized at the start of this talk, I think that we can see traces of all these abilities in our closest relatives, so in other animals, and in particular in other great apes. So there's some evidence that chimpanzees are capable of at least some limited forms of vocal learning, so learn to produce novel signals. There's also good evidence that a number of species are capable of being forced to acquire complex structured grammars. So there's a number of studies where people have very painstakingly trained non-human animals on a subset of a human-like language. Okay, so you can train an animal, given enough time and enough patience, you can train an animal to be able to interpret complex linguistic sequences. Okay. The process by which you can train an animal to do that kind of thing is very laborious. It's very unlike the relatively effortless process of language learning in humans, but nonetheless, you can cram one of these grammars into an animal's mind. I think there's also some evidence that non-human animals, and particularly our closest relatives, have some capacities to make inferences about the mental states of others and use those inferences about knowledge or ignorance in other individuals to shape their communicative behavior. Okay, so in the interest of time, I'm just going to give you a little example of chimpanzees doing something that looks a lot like this, and I'll skip the examples of these other things. Okay, so this comes from work by Katie Slocum and her colleagues, which suggests that chimps take into account knowledge or ignorance of other chimpanzees when they are communicating in the wild. Okay, so to illustrate that, I'm going to show you two videos of from this paper of how chimpanzees respond to a dangerous item in the environment, a snake. So Katie and her team chased chimpanzees through the jungle in Africa for 2 years, trying to engineer situations where a chimpanzee, either on its own or in company, would stumble across a snake. So they had a model snake that they were running around the jungle with, chasing after these animals. And they were trying to engineer the kinds of situations I'm going to show you now. Okay, so this is going to be a solitary chimpanzee coming across a model snake that Katie and her team have laid down. And you'll see its response. There's also some narration, so the person following the chimp is also talking into the camera.
Nambi seeing the snake. Hooing. Hooing. Hooing.
Okay, so it sees the snake, has a massive startle response, and then it produces this very soft vocalization. I don't know if you could hear it at all. This is called a soft hoo. So it's basically a noise they make to themselves when they see something they don't like very much. Okay, so I'll just play that again because it's funny.
Nambi seeing the snake. Hooing. Hooing. Hooing.
Okay, now you can contrast that with what a chimpanzee does when it has company suddenly. Okay, so this is another chimpanzee. It's initially on its own. It's come across the model snake and it's hooing, as you'll see in the video. And then another chimpanzee from its group appears. This chimpanzee turns around and sees the new chimpanzee who's arrived. You can watch its change in behavior when it realizes there's another person there who might not know about the snake.
Musa is on my side. Moving.
Okay, so what they do is they switch from producing these soft hoos that are basically for their own consumption to something that's known as wah barks. These much louder, much more energetic signals, and then they also gaze alternate between the snake and the other chimpanzee. So the claim that Katie and her colleagues are making is that this reflects the fact that they have realized that this other chimpanzee doesn't know about the snake. Okay, so they're doing some inferences about the mental state of this other animal, and then that's modifying their vocal behavior. So they're switching from soft hoos to wah barks in order to inform the second chimpanzee about the presence of the snake. Okay, running this kind of study is enormously time-consuming. So 2 years to get about 25 trials where they managed to construct this kind of scenario. So I think this data is suggestive rather than conclusive, but it does offer some hints that other animals, and in particular our closest relatives, are capable of reasoning about knowledge riggedness in other individuals, reasoning about mental states, hidden mental states, and then using those inferences to shape their communicative behavior. And if you want to be able to learn or use a full-fledged linguistic system, you have to be capable of making those kinds of inferences. And our closest relatives might be capable of some relatively kind of rudimentary inferences along those lines. Okay. And there are similar examples of similar suggestive evidence for the capacity to do learning of complex signals and also representing compositional grammars in non-human animals, and in particular in our closest living relatives. Okay, so what's the idea here? The idea is that our ancestors ended up with these three abilities: ability to learn to produce novel signals, to reason about mental states in others, and to mentally represent compositional languages. And this might not have been a kind of gigantic shift from the capacities that our last common ancestor with chimpanzees had. So maybe evolution only needed to give us a little nudge to push us over the threshold, provide us with the necessary abilities in these three areas to enable the transmission of meaning form mappings. And then once these capacities are in place, that sets off the iterated learning process. And we know that iterated learning produces linguistic structure of the kinds that I talked about in part 2. Okay, so the idea is that the crucial evolutionary event in human history is not evolution providing us with linguistic structure, but rather evolution providing us with the capacity to learn and transmit meaning form mappings. And once you have those capacities, then linguistic structure evolves as a kind of natural side effect of language learning and language use. Okay, what that also suggests, and this is the last experiment I want to show you, is that if we could scaffold the transmission of structural behavior in a non-human animal, say a primate, then systematic structure should kind of automatically evolve. So our claim is that the big evolutionary innovation is the ability to transmit behaviors from individual to individual, the right kinds of behaviors. And once you have that in place, then you kind of get structure for free. And if so, then we should be able to find another animal and help them out, scaffold this transmission process, and then get structure to develop for nothing, just as a result of transmission of that behavior. Okay, so we teamed up with Nico Cladier and Joël Fagot, who are based at the CNRS in Marseille, to test that hypothesis. We ran an iterated learning experiment in baboons. Okay, so this is the CNRS primate facility down near Marseille. It's a facility that's been set up by Joël Fagot. It basically looks like a zoo enclosure where there's a troop of baboons roaming around. On the edge of the enclosure, there are these porta cabins with doorways. And when a baboon's in the mood, they can pop through the doorway and enter the experimental apparatus. Okay, so Joël has trained these baboons to operate touchscreen computers in these booths. They have chips in their arms, so when they reach to operate the computer realizes that baboon's there and actually knows which baboon is there. And they see stuff on the screen, they make touches of the screen in response, and if they get a trial right, they get a food reward. So this is Joël, you can see he's French, and he's explaining he's explaining that if an animal performs correctly on a particular trial, then they get a food reward. They get a few grains of puffed wheat. Okay, that's what the machine dispenses that for them automatically. They can do as many trials as they want, and they like puffed wheat, so they do a whole bunch of trials. And when they've had enough, they leave the apparatus. Okay, so this is an amazing and unique facility, and we used it to set up and run an iterated learning experiment in baboons, passing a behavior from animal to animal and seeing how it evolved. Okay, so this is the behavior we transmitted from animal to animal. It's a very simple, from the baboon's perspective, a simple kind of visual memory task. So what they see on the screen are 16 squares. You can see them there. 4 of those squares are momentarily red, and then they turn white. And the animal's task is to touch the 4 squares that were red. Okay, this video is going to loop in a moment. Every time they get it right, they get a food reward, and that's what she's retrieving from down here. Okay, so that's the correct response. She touched all the correct squares, and so she gets a few grains of puffed wheat. And they just do this over and over and over again. Okay, so visual memory task. Okay, so we have a bunch of baboons doing this visual memory task. At any one time, we have a set of 50 grids that one animal is working on for us. And we're going to pass this set of 50 grids from animal to animal and see what happens to that set of grids. Okay, so our first baboon is working through this set of 50 grids. They see a pattern, they reproduce it. They see a pattern, they reproduce it, and so on and so on and so on. Now, whatever this animal produced, regardless of whether it was correct or incorrect, we take that, we scramble the order of the grids, and we pass the grids that this animal produced as targets for reproduction in a second animal. Okay, so this guy saw this pattern, produced this pattern, and then later on we'll take the pattern that he produced and ask a second baboon to reproduce that pattern. We take this set of 50 grids and we pass them from animal to animal. Just through that kind of familiar iterated learning process. And what we're interested in, here we've scaffolded transmission of a kind of potentially complex behavior in these animals. And what we're now interested in is what happens to that behavior. So our prediction is that iterated learning will take over and structure will evolve now that we've set this transmission process in train. Okay, so I'm going to show you the results of one of these chains of transmission. So this is a set of 50 random grids that we initialized one of these chains of transmission with. So here are 50 grids laid out in 5 rows. And you can see random grids are basically just basic. 4 randomly selected squares are red. In among these grids, I've highlighted a couple of unusual grids. These are called tetrominoes, so you'll recognize them from the computer game Tetris, if you were into that. These are 4 orthogonally connected squares, and they're quite rare, so only about 1 in 20 random grids is tetrominous, has this particular configuration. Okay, so one animal worked through these grids and tried to reproduce each of them, and it produced a set of grids that looked like this, which we'll call our generation 1 set. Then we take this set of 50 grids and ask a second animal to reproduce them, and that second animal produces this set of grids. And then we can just pass the set of grids from animal to animal. See how it changes as it goes. So generation 8, 9, 10, 11, 12. Okay, so by the time this set of grids has been filtered through 12 baboons, it's radically changed. Tetrominoes have gone from being incredibly rare to extremely common. So now basically all the grids in the set are tetrominoes or near tetrominoes. Okay, so the set of behaviors that we gave these animals has evolved as a result of being passed from animal to animal. And it's evolved a kind of systematic structure. Okay, so what we're looking at is the emergence of a system where reproducing one element from this set facilitates the reproduction of other elements from the set. There are a number of pointers in our data that what we're seeing is the evolution of a regular system of behavior. And one of them is that if you run this process again, you run a second independent chain of transmission, you'll get out a different kind of structure. So you'll notice that this is the result of generation 12 in one particular chain. You see lots of S shapes and T shapes. We ran multiple such chains, and each chain produces a different distribution of grids at the end. So this is the result of, this is a generation 12 grid set in a different independent chain. And now you'll see there's hardly any S's and T's, and instead there's lots of L shapes and lines. Okay, so you wouldn't expect that if the grids were evolving independently. So what this suggests is that reproducing one pattern from a set of regularly structured grids, a set of grids that resemble each other, facilitates reproduction of other grids from that set. So we're seeing the evolution of a kind of regularly structured system. So the structure in this set of grids is radically different from the kind of regularities we see in natural languages, but that's because of the kind of possibilities of the behavior that we gave these animals. So iterated learning produces regular systematic structure, happens in humans, and we can show it, and it turns out it also happens in monkeys. So it's not, the emergence of structure is not dependent on uniquely human kind of structure building capacities. It emerges as soon as you facilitate the transmission of structurable behaviors from individual to individual. Okay, so just to wrap up, we think we can show that fundamental structural properties of human language emerge from this cycle of learning and use by which real languages are transmitted. I think that suggests that the uniqueness of language is due not to some unique human structure building capacities, but rather to our unique capacity to learn and transmit meaning form mappings. That's the capacity in humans that we have to explain the evolution of. That's the major evolutionary event that happened in our lineage, but not to the other great apes. Interestingly, I think we see echoes of the capacity that underpin these capacities in humans and our closest living relatives. So evolution might have only had to give our species a little nudge to push us over the threshold and give us the necessary capacities to set that iterated learning process in train. Okay, so I think there's a bunch of open questions. It'd be nice to know what selection pressures pushed humans over the edge and drove us to develop these unusually elaborated capacities, these 3 capacities. We're working currently on how languages complexify, so how we go from these very simple languages that we're getting at the moment to more complex and interestingly structured linguistic systems. I'd also be interested in how the genesis of language influenced our subsequent evolution and might feed back into the evolution of the capacities that are required for iterated learning. So I think there are enough open questions to keep us busy for the next 20 plus years at least. Okay, thank you for your time and your patience.